The fundamental theorem of calculus, part 1. Most mathematicians consider the fundamental theorem of calculus as the most important discovery in the history of mathematics. This relationship between differentiation and integration provide a critical connection between the two fields, which first appeared unrelated. The fundamental theorem of calculus has two parts. In the previous chapter, we discussed part 2. This chapter, we will cover part 1. Consider the following graph. What does f of x represent? F of x represents the area under the curve from 0 to x, which can be written as this definite integral of f of x equals the integral from 0 to x of t squared dt. If f of x is equal to the integral from 0 to x of t squared dt, then using our previous knowledge of integration, we can evaluate f of x. If we think of it in terms of antiderivatives, the antiderivative of t squared is equal to 1/3 t cubed as we evaluate the upper bound of x and the lower bound of 0. We can replace t with x and 0, which gives us 1/3 x cubed minus 1/3 0 cubed, which is equal to 1/3 x cubed. Therefore, f of x is equal to 1/3 x cubed. Using the fundamental theorem of calculus part 2, we substitute and simplify. Now, taking this one step further, let's calculate the derivative of f of x. F of x is equal to 1/3 x cubed, and f prime of x is equal to x squared. Let's take a look at what we have so far. Notice any connection between the integrand, f of x is equal to the integral of 0 to x of t squared dt, and the derivative of the evaluated integral, which is f prime of x equals x squared. The derivative of the integral is equal to the integrand with x substituted for t. Here we have t squared, and here we have x squared. This connection led mathematicians to the discovery of the first part of the fundamental theorem of calculus, abbreviated FTC Part 1, which states if f is continuous or is a continuous function on the closed interval from a to x, then the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. The derivative of the integral is equal to the integrand with x substituted for t. In common terms, if taking the derivative of an integral evaluated from a constant to x, you can simply replace the variable in the integral with x for your derivative, as denoted from this figure right here. This only applies when the lower limit of integration is a constant and the upper limit is x. As we saw previously, this occurs because evaluating the integral at a constant and then taking the derivative results in 0 and does not affect the final result. Let's look at how this theorem works with another function. In this case, we are asked to find the derivative of g of x, which is equal to the integral from 3 to x of 1 minus t squared dt. Now notice the problem asks you to take the derivative of an integral. We could have done a series of work where we found the integral, evaluated it from 3 to x, then differentiated it. But earlier we discovered that the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. So all we need to do is substitute x in for t, and we know that g prime of x is equal to 1 minus x squared.